Hello everyone, this is my third video lecture on the concept of vector spaces, and I'm going to talk about linear combinations of vectors, linear spans of sets, something called as generating sets. Okay, so let's begin. I'll start with linear combination. What do you mean by linear combination? Let me begin with an example. Let's suppose that we have a vector, say 2 comma 1 with us. Let's draw the vector. So this will be 2 and this will be 1, and this will be a 2 comma 1. The point is the vector, which is represented by this arrow, that's 2 comma 1. Let's take another vector. Let's say we have say 1 comma minus 1. So 1 comma minus 1, 1 is here and minus 1 is here, so 1 comma minus 1 is this point, and when you represent it by the arrow you get this. Now let's say we double the vector, that is, let's say we scalar multiply the first vector by 2. So what would we get? We will get something like this. We will get 2 times 2 comma 2 times 1, which will be 4 comma 2. So the resulting vector, as we saw, it will be 4 comma 2, 4 is here and 2 is here. So as we see that this vector is doubled, so this is the new vector, and this vector is our vector 2 comma 1. What happens to the vector v2 when we take, say for example, 3 times of the vector v2? So we will get 3 times 1, which is 3, and 3 times minus 1, which is minus 3. So where is 3? This is your 3 and this is your minus 3. So this is your new vector, which is simply this vector stretched in the same direction 3 times. Okay, now what happens when you take the resultant of these two vectors? As we know by the parallelogram law that we can make a parallelogram, and the diagonal of the parallelogram will be the resultant vector. This new resultant vector is called as the linear combination of the vectors v1 and v2. So this is your 2 times v2, and this is your linear combination. So we can also theoretically find out what our v is. In this case, it is 2 times v1 plus 3 times v2, which is nothing but 4 comma 2 plus 3 comma minus 3. This 4 comma 2 comes from here, and 3 comma minus 3 comes from here, and what do you get? You get 7 comma 4 plus 3 is 7, and 2 minus 3 is minus 1. 7 comma minus 1. Let's see whether what we have found is somewhat close to this. So this is 1 2 3 4 5 6 7. This point is 7 and this is minus 1. Yes, so we are almost there. So this new vector is the linear combination of v1 and v2. Once again, so what do you mean by linear combination? Linear combination of vectors v1, v2 and so on up to say vn belonging to v, which is simply a vector space, is nothing but the sum of the scalar multiples of these vectors. I should say simply a vector given by sum of the scalar multiples. What do you mean by the scalar multiples? It means that v1 is multiplied by some scalar. Let's call it as alpha 1. v2 is multiplied by some scalar. Let's call it as alpha 2, and so on up to vn. This new vector is called as the linear combination of v1, v2, and so on up to vn. Let's look at an exercise. Suppose we have something like express maybe a vector v 1, 3 which belongs to the xy plane as a linear combination of, say, v1 is equal to 1, 2 and v2 minus 1, 2. So in this case, in this type of exercise, we are expected to find out the coefficients of v1 and v2 when you write v as a linear combination of v1 and v2. So how do we begin? Let us simply write it as, v is equal to a times v1 plus b times v2, where a and b are simply scalars. Now let's begin the problem. Simply we substitute the value of v as 1, 3, value of v1 as 1, 2. So you have a times 1, 2 plus b times minus 1, 2. So if you take the scalars inside by using component wise scalar multiplication and then you do the sum, finally what we will be having will be a plus minus b, and that will be a minus b. And in the other case, the second component would be a into 2, which will be 2a, plus 2 into b, which will be 2a plus 2b. So comparing this with this, we have a minus b is equal to 1 and 2a plus 2b is equal to 3. Simplifying this further, we will get a system of equations as a minus b is equal to 1 and 2a plus, that should be a plus b is equal to 3 by 2. So we get a system of linear equations which can be solved simultaneously. To get, say, if you add these two equations, you would be landing up having 2a is equal to 1 plus 3 by 2, which would be 5 by 2, and hence you have your a as 5 by 4. Substituting this back into any one equation will give me b is equal to 1 minus 5 by 4, which is 1 by 4. So finally we have our answer. We can write our v as the a was 5 by 4. So you can have 5 by 4 times v1 plus 1 by 4 times v2. Let us now look at the meaning of linear span. That's our second definition. So linear span. So when you talk about linear span, we consider a set. We talk about linear span of a set, of course, in a vector space. So let us say S is any subset of the vector space. I'm not saying that this set S is a vector subspace. I'm simply saying that this set S is any set from the vector space S. This is any subset. So what do you mean by the linear span? So the linear span of S is defined as L of S as equal to the set of all linear combinations of the vectors in S. And if you notice here, when I say linear combinations, I have stopped at some n, but this n is not fixed. This n can be any natural number. And what are these alpha i's? These alpha i's are simply scalars taken from the set of real numbers. So you can also say that it is a set of all finite linear combinations of vectors from S. So let's deal with this with the help of an example. Let us say we have the vector space V as R2, our favorite example, a vector space over R. Let us consider our S to be the set 1, 0 and 0, 1. If you notice, this 1, 0 and 0, 1 is nothing but, we'll make it with the help of a red color. So this is 1, 0. So with the help of, if I represent it with an arrow, it will look something like this. This is 1, 0 and this is 0, 1. What would happen if I take the linear span of this set? The linear span of S would be the set of all finite linear combinations of the vectors from S. Now since there are only finite vectors in the set S, I can simply write it as set of all linear combinations. Notice here that I am using the summation notation. I can also write it as alpha 1, 0 plus alpha 2 times 0, 1. These are the vectors in S and these are the scalars. I can also replace the alpha 1 and alpha 2 by X and Y. There is nothing special. Oh, I made a mistake over here. This should be the set of real numbers. The scalars are taken from the set of real numbers. So what would you get if you do something like this? So if you take the x inside, you will get x times 1 is x and x times 0 is 0 plus y times 0 is 0 plus y times 1 is y. And with x and y are taken from the set of real numbers. And if you notice, if you still have the vector addition sign over here, if you combine these two vectors with the help of the vector addition, you will get x plus 0, which is x, and 0 plus y, which is y. Okay, so you get a set of all x, y where x and y belong to R. But what is this set? This is simply R2. This is simply R2. So what you got here is L of S is giving you the entire space R2. But what would happen if we simply consider the set, say for example, you consider S as the vector 1, 1. Let's draw that. The vector 1, 1 can be represented with the help of this dot. This is 1, this is 1, and with the help of this arrow. This set is finite, and hence when you write the linear span of this set, I can write it as set of all linear combinations of the vectors in S. But there is, since only one vector in S, we cannot write it as a summation because there are no other vectors to add. So L of S would simply be the set of all scalar multiples of the vector in S, which can be simply written as alpha times 1 comma 1, where alpha belongs to the set of real numbers. There is nothing special about this alpha. I can replace this alpha also by the letter T. So what would I get? This is simply set of all T comma T, where T belongs to R. But notice that this T comma T, if you keep on varying as any number from minus infinity to infinity, you will get an entire line of this form. Now this is nothing but the parametric equation of this line. So you're not getting the entire space, but you're getting a line in R2. Okay, so there is something special about this set S. Such kind of sets are called as generating sets. Of the vector space. We call it as a generating set because it generates the entire vector space. So S subset of V, a vector space over R, is said to be a generating set if L of S gives you the entire, I was about to write there R2. Since I'm talking about a general vector space, I should write there V. So any set is said to be a generating set of the vector space if the linear span of that set is equal to the entire vector space. We can have plenty of examples of generating sets for any vector space. For that matter, when you consider V is equal to R2, we had already dealt with this generating set 1, 0 and 0, 1. You have been dealing with this set from the time you have been doing 2D geometry. The only difference is that you used to call these vectors as the vector I and this vector as the vector j, I cap and j cap, which were nothing but the standard unit vectors, mutually perpendicular to each other. You can also see that when you consider your S as say the vector 1, 1 and the vector say this vector would be minus 1, 1, even this would be a generating set. You can say that it generates the entire vector space R2. Even for that matter, when you consider the vector space R3, you can have your S as a very standard example as 1, 0, 0, 0, 1, 0 and 0, 0, 1. This would be a generating set of the entire vector space R3. Okay, so we see that when you start, given a vector space, when you're saying that your S, let's take R2 as an example. When you take S as simply the point situated at the center of the plane, which is the origin, you notice that when you take L of S, it will be the set of all scalar multiples of this vector. But if you take the scalar multiples of this vector, you know that alpha will be absorbed inside, and finally you will be left with the same set. So L of S is nothing but the origin. If you consider your S as say the vector 1, 1, you saw that L of S turned out to be the line t times 1 comma 1 where t belongs to R. This was nothing but the line that passed through the origin. And for the first one, it was nothing but the origin. What would happen if you take S as 1 comma 0 and 0 comma 1? So if you recall, L of S was found out to be R2, the entire space. So you got the entire space R2. So you see that L of S grows in a linear fashion, whatever your S is. So you can always make a guess about L of S. And the guess is that L of S always turns out to be a vector subspace of the vector space V. Of course, if your S is a subset of V. And this is very much trivial to check.